Welcome back. We're going to switch gears a bit, and the next few lectures are going to be about the biology of life, talking about its origin, its evolution, and then ending with speculation about life elsewhere in the universe. In the next couple lectures, I'm going to be talking primarily about biology. Now let me give you a warning. I'm not a biologist. I'm an astronomer and a physicist. I believe most of the things, or hopefully all the things I'm telling you, represent things that are consistent with our current understanding of biology. But let me begin with a little bit of an apology that if there's something you catch that doesn't seem right in this section or in any other section, let me know and we'll post something about it and make sure we get that right. So let's begin by tracing our biology. What we want to do is begin by talking about the simple ingredients that make up amino acids, nucleotides, and the other basic building blocks of life. Next, we're going to go from amino acids to proteins, and then from proteins to cells. So let's begin our journey with the basic building blocks. And the key building block for organic life is carbon. Carbon's a really interesting element. Carbon has really strong bonds that let you build complex molecules. And we have these very strong carbon-carbon bonds between pairs of carbon that serve as a building block that lets us construct very complex molecular structure. Not only can carbon form strong bonds with carbon, carbon can also form strong bonds with hydrogen and with oxygen. That lets you build complex molecules. And when you bond carbon with oxygen, you can form carbon dioxide, and that's a gas that lets you move easily through materials. When you form carbon with hydrogen, you can form methane. One measure of the richness of carbon, when you make a list of all the molecules that we know of in nature, and you make a list of the organic molecules, those are ones that bond with carbon, and the inorganic molecules, those that bond with all those other elements in the periodic table, but don't bond with carbon, there are 50 times more organic molecules than inorganic molecules, molecules that don't contain carbon. So carbon's structure is such that it really lets you build complex biochemistries. And that's why we think of it as the basic building block for life. Another key part of life is liquid water. On Earth, it is essential for biology. All biological systems are water-based on Earth, and water also has some really neat chemical properties. Here is a water molecule, and you'll notice, unlike carbon dioxide, which was a nice linear molecule here, water is bent, with the hydrogens forming almost a right angle relative to the oxygen. Because of this, it is a polar molecule with a large net negative charge on this side and a large net positive charge on this side. As a result of this, in water, there's a lot of long-range order. If I add another water molecule to this picture, it's going to want to line up with the hydrogens on this side, with their positive charge close to the negative charge of oxygen, and the oxygen on this side. And the next water molecule would want to line up here with the oxygen on this side close to the hydrogen. That long-range order is a relatively long-range order is unusual in water and in liquids, and gives water some of its interesting properties. Because it is a polar molecule like this, it's a very flexible solvent, and it has lots of interesting chemistry. Our cells and our bodies are mostly made of water. Water being an excellent solvent means it has some very interesting properties in how it interacts with other materials. There are some molecules or molecular endings that are hydrophilic. They like water. OH, COO, sugar, polar solvents. Others don't like water. CH3, CH2s. And when we do that, when we put these things in water, what we find is, so these are molecules put in water. This end of the molecule is hydrophilic. It might be an ending in the molecule like that. This part of the molecule is hydrophobic. It doesn't like water. So you can see all these molecules will line up like this in this lipid and form a very nice layer with the hydrophilic or water-liking parts facing out and the hydrophobic facing inwards. As a result, water is a natural material for forming a bilayer like this. Given these elements of water, carbon, other elements like silicon and nitrogen, we can assemble the four basic building blocks of life. These are relatively simple molecules that we will combine together, or life combines together, to make things like protein, DNA, and cells. These four basic building blocks are amino acids that combine to make proteins, nucleotides that combine to make nucleic acids, carbohydrates, and lipids. So you're going to build these up out of relatively simple building blocks. We combine sugars to make our carbohydrates, our polysaccharides, fatty acids to make our lipids and membranes, amino acids to make proteins, nucleotides to make nucleic acids. These basic building blocks are made up of a handful, 10, say, atoms to make up these simple elements here. These larger units of the cell, things like proteins and nucleic acids, are going to be made up of thousands of atoms. And what we'll see when we look at our biology really consists of taking simple building blocks and using them to make more complex structures. This is what might be called the Lego principle of biology. With Legos, you can take simple building blocks and build complex structures. All of biology is made up of a handful of these simple building blocks. 20 amino acids, 5 nucleotide bases, a few sugars and fatty acids, and out of these simple pieces, we assemble more complex structures. In fact, a lot of nature is like this. We build up atoms out of just protons, neutrons, and electrons. And from those three basic building blocks, the protons and neutrons are actually made up of quarks, but out of protons, neutrons, and electrons, we can assemble atoms, and there's lots of different types of atoms. And out of the atoms, the 100 or so atoms, we can assemble thousands upon thousands of different molecules. Nature does not make use of most of those molecules. It just chooses a handful. And from that, from those simple Lego-like pieces, it builds up all of life. And all of life on our planet seems to use this simple principle. And one of the things that we speculate is that this simple principle might work elsewhere. And when we see other life forms, they might be like these different children's toys. Some might be made of Legos, and others of Kinects, or out of erector sets. But they all have the same element of taking simple pieces, building them up to make more complex structures. So let's talk about some of these building blocks. Let's start with amino acids. Amino acids are the building blocks that we use to assemble proteins. Amino acids are relatively simple. A typical amino acid is going to be made of between 13 to 27 atoms. The atoms that we use to assemble it are carbon, oxygen, nitrogen, hydrogen, and sulfur. These are among the most common elements in the universe. There's lots of them. And the amino acids themselves all have a very similar form. They all are made up of a carbox ending that loses a hydrogen, so it's ion. So we have the COO minus combining with an amino end that takes on a proton, and these combine to form a structure like this. And these ends then plug together to form a peptide bond, and we can connect these amino acids together to make more complex proteins. Now, one of the interesting features of amino acids is most of the amino acids have different symmetries. We can think of them as being either left-handed or right-handed. And the chemistry of these left and right-handed amino acids are similar, but we can't assemble left and right-handed structures together to make nice chains. If I want to glue the carbox and amino acid ends together, so I'm going to line up another one here and another one here and another one here and another one here. If I want to tie them all together like that, they're going to have to be oriented the right way. Nature chooses to make all of life out of only left-handed amino acids. Why is that? We don't know. When life originated, were there originally a left-handed forms and right-handed forms and only left-handed forms? We don't know. But we think that this is perhaps a big hint about the origin of life itself. Here are these basic building blocks that nature chooses, these amino acids. There's actually 170 amino acids available in nature, but only 20 are chosen to make up life. And we don't know why those remaining 150 aren't used. And of those 20, as I've mentioned, 19 of them are left-handed. One of them actually has the shape of being symmetric. But nature chooses a relatively small set of these amino acids, and they're shown here, to assemble all of life. So now that we've seen what the basic building blocks are, I want you to think back to our earlier lectures where we talked about Mars and ask, are the basic building blocks of life available on Mars? If all it takes are the right elements, does Mars have them? Think about that for a moment, and then we'll come back.